So our last problem here, example 3, you want to graph the equation r is equal to e to the power of theta over 5. So this one definitely looks different. It doesn't look like anything what we had before with our table of equations, but nonetheless, we can try and determine whether it is symmetric and go ahead and plot it. So, as always, we are going to check for symmetry. First things first, we're testing for our polar axis. Remember, we're replacing theta with negative theta. If we do this, we end up with just e to the power of negative theta over 5, which you could go ahead and rewrite this as 1 over e to the power of theta over 5, but either way, it is different. It does not give us the same value, so this fails. And remember, since it fails, it just means that we don't know whether or not it is symmetric about the polar axis. Then we want to try for the line pi over 2. So we're replacing theta now with pi minus theta. So when we replace this, we're going to have e to the power of pi minus theta over 5. There are definitely different ways that you could end up writing this, but either way, it does not give us the same equation as before, so we can't determine if this is symmetric either since it fails. Then lastly, we want to test for our pole. So we're testing r turning into negative r and theta turning into theta plus pi. So with r turning into negative r, if we just give r a negative sign, we get negative r is equal to theta over 5, which then just simplifies to r is equal to negative e to the power of theta over 5, which is obviously not the same. Now we can replace theta with theta plus pi. When we do, we end up, we'll start writing here. We end up getting a e to the power of theta plus pi over 5. Once again, there's a few different ways that we could definitely rewrite this, but it still doesn't give us the same value as we had before. Checking for symmetry is very helpful when working with trigonometric functions, but if it's not a trigonometric function, it's probably a pretty good chance that it doesn't have symmetry, but you always want to check and just make sure anyway. So we see that it failed every one of our symmetry tests, which just means that we're not entirely sure if it's symmetric about anything. So just to sum this up, all symmetry tests failed, and we can determine that there will be no value theta for which r is going to be equal to 0. Since we have r is equal to e to the power of theta over 5, e will never be equal to 0. It's an exponential function and it's a property of it. If it's never equal to 0, then that means that there is no value of theta that would make r equal to 0, which means that whatever our point is not going to go through the origin or the pole. So our equation, or our graph, doesn't go through the pole. So that's something that we can identify right off the bat. We can identify a few other things as well with our equation. It's just going to help us when we actually go to graph. But a few of the things that we can check for is that from our equation, we have that r is positive for all values of theta. Once again, this is a property of the exponential function. So r is always going to be positive for any value of theta. We also get that r increases when theta increases. R is going to approach 0 as theta approaches negative infinity. And r will approach positive infinity as theta approaches positive infinity as well. So this is just going to help us graph, and you'll see why once we start graphing it. So to find points, we want to use a calculator. So just like before, we want to draw out our table here where we're going to have theta and we're going to have r, where r is equal to e to the power of theta over 5. We're going to include quite a few, quite a few values here. Oh my goodness. Come on, there we go. We're going to include quite a few values here. We just want to make sure that what we're doing is going to be correct. So let's go ahead and test from 0 to 2 pi, but also let's go ahead and check from negative 2 pi to positive 2 pi. We want to include a wide range here. So we're going to use negative 3 pi over 2, negative pi over 2, negative pi over 4, 0, pi over 4, pi over 2, 3 pi over 2, and then lastly 2 pi. Pretty close there with measuring out the length of this table here. So the only way to find these values is by plugging this into a calculator. There's no way that you're going to figure out this by using the unit circle or anything like that. So plugging these values into a calculator and solving for these values are how we're going to get these. So I strongly encourage you, if you are watching this video, to pause the video, go ahead and calculate all of these values on your own, and then just make sure that they are correct. All right, so these are going to be all the values that we get from our table and plugging these into a calculator. I did realize that I forgot the value of theta is equal to pi, so I have included that now. So these points are going to give us all the points that we need for our polar coordinates. So let's go ahead and start trying to graph these points. We're not working with any symmetry, so we're just going to pick our one color here. And we can see that when we go to start plugging in these values, it's actually going to be very hard to write in any of these values. That's why we picked a larger range. So it's actually hard to graph these. So we're going to start here. So we're actually going to start at theta is equal to 0. So when theta is equal to 0, we're going to get that our value is 1. So we're going to start at this point. Then our next value at pi over 4, we're going to have 1.17. So honestly, just a little bit greater than 1. Then at pi over 2, we're going to have 1.37. So once again, just kind of barely higher than 1 at this point, not even quite 1/2 yet. At pi, we're going to have 1.87. So almost 2, but still not quite there. At 3 pi over 2, we're going to end up with a 2.57, so just about halfway between the 2 and the 3 mark. And at 2 pi, we're going to end up with a 3.5. So coming around again, you know, this is 0 to pi. Let's change that up there. So this is about 0 to pi. We're at about 3.5. So we're going to connect these points. When we do, what we see happening is that we are getting larger and larger with our larger values of theta. And it's not a perfect image there, but we can pretty much assume anything greater than 2 pi is actually just going to keep increasing. So we can draw an arrow like this. Then for all those values that we stated was just going to be too hard to graph and they had negative values anyway, we're just going to represent these by actually just drawing in an arrow, signifying that we're going to get closer to 0. And what we end up getting here is a spiral. So this is going to end up being a spiral. And we can determine that it's a spiral because we're seeing that r is going to go to 0 as theta goes to negative infinity, and r will go to infinity as theta goes to infinity. So we have this spiral image here. It's not really one of our typical equations that we see with our normal graphs, but it is something else that is important to look out for. So the curve that we just went over, this is called the logarithmic spiral. It can also be written as theta is equal to 5 times the natural log of r, so that's why we call it the logarithmic spiral. It spirals infinitely both towards the pole and away from it. For a polar equation involving only a sine or cosine function, you can use the tables from above to identify the shape, determine the periodicity and symmetry, and then plot half the points to graph quickly. So just reiterating that if you want to graph an equation quickly and it uses sine or cosine, that's the key, it has to use sine or cosine, you can very quickly just identify the shape based on the equation using the tables. You can determine the periodicity depending on what trigonometric function it is, and then solve for the symmetry. And once you have that, all you need to do is really plot about half the points that you would normally need to and reflect about wherever you have symmetry of. For more examples of these problems, there are lots of examples in the book that you can definitely go over. For the sake of time, we cannot go over every single type, but there is an example for every single type of the different kinds of equations and different shapes you can end up having. So they are in the book. So please look there if you would like any extra help or review or just want to go over more. So all right, that wraps up our section 9.2. So I'll see you all again in section 9.3.